Hello, and welcome to today's webinar, UAVs from Flying Drones to Doing Business. This is brought to you by our sponsor, Septentrio. I'm Kelly Limpert from North Coast Media, digital editor for GPS World Magazine, and I will be your event manager. Before we begin, I'm going to go over some ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the entire presentation. Just type in the text box at the bottom left, then click Submit and place your question in queue. You can also submit questions via Twitter by using the hashtag GPSWorldWebinar. Questions that were submitted during registration have already gone to our panelists and may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World Magazine or in one of our e-newsletters. We strive to answer as many questions as possible. If you experience any technical difficulties during today's event, use the same Q&A box at the bottom left to tell us about your issue and click Submit, and assistant producer Joelle Harms or I will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. You can get to that page now and bookmark it by clicking on the GPS World logo in the top left-hand corner of your console. A link to the on-demand recording will also be emailed to you when it is available. And with that, I'd like to turn today's event over to our moderator, GPS World editor Alan Cameron.
Thanks, Kelly. Hello, everyone around the world. I see from our attendee list that we do have attendance from a number of countries spanning the globe. Welcome to today's webinar, UAVs from Flying Drones to Doing Business. We have 4 speakers for you today, and they will all come at the UAV subject from their differing perspectives. We have a GNSS manufacturer, our sponsor, Septentrio, and by the way, thanks to Septentrio for making this webinar possible. We have Gustavo Lopez from Septentrio, and again, a GNSS manufacturer working to put positioning navigation ability aboard UAVs. We have 2 speakers, Jan Leysens and Francois Gervais, who are working directly with drones with UAVs in their own companies, and they will talk about various aspects of their business facilitating use for end users, particularly in safety of operation and use in surveying. And finally, we have a researcher, Zach Casas, who's going to tell us about his work using drones, UAVs, in areas where GNSS may not be available. Of course, this is a growing topic and a constant concern whenever GNSS is used because it is not available everywhere. What to do when it isn't. Finally, the last act of this webinar is you. We'll turn to your questions during the last 10 or 15 minutes of the show. And as Kelly said, I've collected a number of the questions that you submitted when you registered for the webinar. We'll turn to those first, and then we'll also hope to gather some live questions that you may be submitting while the webcast is underway. Now I want to turn the floor over to Gustavo Lopez from Septentrio, and take it away, Gustavo.
Hello, everybody. Welcome to the webinar for enabling UAS platforms for business. My name is Gustavo Lopez. I'm the product manager for UAS mapping and surveying applications here at Septentrio. For those of you who don't know about Septentrio, Septentrio is a company manufacturing high-end GNSS receivers in different types of applications, from machine control to even mapping, surveying type of applications. Surely on this webinar, we want to focus on the experiences that we have had with the UAV market and especially with integrators in our portfolio. So before I want to explain to you what I call basically a new kind of drone, this is in this slide what I want to represent is the jump from the left towards the right. In the right side, we have basically all the different applications that are coming into the market in order to have a commercial business out of your UAV integrations. This can be from agriculture, mining, inspection. So there are different applications already coming into place. Surely that is thankful to the fact that people are focusing rather than on the pilot, they are focusing now on the user side. That means that basically there are the needs for having the data out of the drones. It's not necessarily anymore on the pilot where basically you just were just flying the drone. Now you really want to make some use of the data for the different applications. This is happening thanks to the different technologies that are available. You have different sensors today in the market. So the innovation is really bringing all these opportunities. Of course, companies have the challenge to put all this technology together, and also they have some challenges on the social aspect. I mean, there is, of course, a legislation aspect, and there are many people that are still skeptical about the technology, So the commercialization of drones is already a reality. In this webinar, we will have already some presentations on that side, so I'm very glad to be collaborating with them. And from our experience, basically what we see is that people are in need of bringing focus into the data and the services. And not only that, people are in need of a reliable positioning system. This is what we notice, and that's why people are approaching us a lot. And this is not only for the intrinsic part of the application side, there is also a need for safety in order to basically help in those social challenges that are in the market there. So when we are talking about a reliable positioning, that means that we need to bring some technologies, and of course we have high-end GNSS receivers which can help you quite a lot for having a centimeter or a reliable accuracy of the system itself. You have to take, however, certain considerations once that you are integrating all that technology into the UAV. I have grouped those into three major clusters. The first one is what I call the GNSS performance. This is basically the link towards picking up the right GPS of choice. There are, of course, consumer-grade GPS receivers, which will already solve certain of your applications, but as I mentioned, people are in need of reliability and of accuracy. So that means that there is basically a large game of basically picking up the right technology for your position inside. The second aspect is what I call the system. If you are integrating a UAV drone, there are different aspects which could go from the antenna side up to the shutter of the camera, and different aspects that you need to take into account once you are bringing the high-end GNSS receiver into the UAV application. And the last one, which is the data flow. You have to think that the final customer is in need of an easy-to-use application in order to bring that possibility of the business and a success out of that application in there. Let me start with the performance side, and I think most of you already know there are different RTK technologies. However, many people think, okay, a drone is working always in an open environment, so it should be quite okay. However, that's not the case. You have to think that a fixed-wing drone might be actually doing some turns and banking, so that means that your signal availability is not always present. The same for an inspection drone, as you can see here in the picture. It's actually working next to obstacles, so it's basically very important to pick up the right RTK technology. And you have to think that there is, of course, a multi-frequency type of technology that actually will be able to solve the solution, and there might be some others that actually are not yet to that level. The other aspect is interference, and this is actually where I want to focus a bit more my presentation. Jamming is a real issue, and I think the considerations of jamming are really important in UAV market especially, and I will go into that. There are two sources of it. The first one is, of course, an external, which can be basically some jammer type of technology. And the second one is the self-interference that you can be causing in the UAV drone. I will go into expanding this, but basically what happens once that you have jamming, you will have signal degradation. And with that signal degradation, that means that you will lose your navigation data, you will have no position, or actually you might even have the wrong position out of the UAV application. That's definitely not wanted. So external interference. As I mentioned, the concerns for people are really increasing a lot, and in particular in the UAV applications is really important. You have to think that the interference signals actually travel much further than what you could have basically in a ground navigation system. This is basically over the air. So, and of course, there is also different sources of this jamming. One of the most common that is happening a lot is, of course, in terms of jammer units. Here is an example of a $50 chirp jammer that you can basically buy online, and it can give you quite a lot of problems in this use case. Actually, you can see that we have a flight, and we could actually jam the UAV up to 1.4 kilometers away. So it's actually a very important problem for UAV integration. For self-interference, and this is a very good analogy here. You can think it as you have your GSM, and if you have your GSM next to your radio, basically you will have some interference. The same is happening in a UAV, and actually even more. This is the biggest problem that we have seen with our UAV integrators. The electronics are so compact. You have basically very little space inside the UAV. That means that you have your engine, your servers, your telemetry, of course your payload, could be a camera, could be a storage, and all these aspects are actually generating some noise, electrical noise, that is affecting your GPS antenna. And that basically, it will also affect your signal, and you will have the same problems mimicking something similar to interference part. So this is also very important. But I have good news for you. There are technologies that can help you to solve these issues. For the self-interference, surely different high-end GNSS manufacturers are bringing in different technologies. Interference monitoring is the best technology that you can find in order to detect where is your interference coming from. Is it coming from my camera? Is it coming from my antenna? Can I move my antenna? So once that you have identified the source, then you can apply some basic good integration practices such as shielding or others in order to mitigate that effect. In the right side here, you can see a spectrum plot. This is a tool set from Septentrio, which allows you to very easily monitor the interference that you may have inside the UAV application. External interference. For external interference, there are technologies, and basically this is based on algorithmic parts, which could be based on software, but also on hardware level, in order to do the automatic interference mitigation. And this is actually an important challenge, not only for the UAV integrators, but of course also for the GNSS manufacturers. The technology that you need here sometimes could involve hardware, so not all the different GPS receivers that are in the market could actually have the same type of solutions. In the left, you can see a plot, and in the plot actually you can see how the mitigation was resolved for a chirp jammer, the chirp jammer that I showed a few slides ago. So it's very important to have this technology into consideration once that you are integrating a UAV. System considerations. So for system considerations, well, the shutter synchronization is very important. Once that you are taking a camera and you want to synchronize that to the GPS event, if you do it in the wrong way, you might have errors from 70 to even 140 centimeters error. So for customers that are looking for a real centimeter accuracy, this is also quite important. Power consumption. The power consumption, even if some people might underestimate the power consumption of the GPS receiver, because it's actually one of the elements of the whole system, it could also give you some effects. Why? Because there is heating in the entire components of the UAV, so that actually can also cause problems in the battery life of your the UAV system. The antenna. If you are picking up an antenna, could be, of course, in order to bring extra constellations such as Beidou, such as Galileo, but the weight and the shape of that antenna can also have a very important effect on the power consumption. So it's really important as well as a consideration. Vibration, of course, another one. Not all the drones are very static or very smoothly flying. So there is also algorithmic technology in the high-end GPS receivers that can help you to smooth these effects as well. And the last one I have is the work data flow. You have to take into consideration that for the whole mapping flow, you might need to consider certain technologies. Is there a library that can allow me to do an offline processing of my pictures? In this example, for instance, Septentrio has GeoTags, which is one of the offline solutions that can help you to do that easily. And it's a library, so it's very good that you could integrate that in your own components of your software side. So this is important. And the last one is the coordinate transformations. We have seen that many people have problems on this aspect. Why? Because you have different sources of coordinates. Can be from the rover, from the base antenna, and all they might have different datums or projections. So it's very important to take it into consideration. So this brings me to my conclusions. Professional UAV applications require reliable positioning, and of course, high-end GNSS receivers is one of the solutions that we are discussing here. Your job is basically the business application. You know what your customer needs in order to bring a successful flow of the data, but it's the responsibility for a GNSS manufacturer to bring you with technology that can effectively mitigate the issues that you might have with interference or other aspects, to provide you with expertise, because of course you have a system and you need the help from somebody there. And lastly, you need components that are easy to integrate for your own workflow so that you can create the full application business for the data flow and satisfying the user need here. So that's all from me. I hand it to you, Alan, so that we can continue with our speakers.
All right. Thank you, Gustavo. Gustavo mentioned, as you heard, the problem of interference in UAV operation, and we will return to that at the end of the program. I see a number of audience questions deal with interference, spoofing, and jamming. We're going to turn now to professional use of UAVs and different situations and problems that may be encountered as you actually try to fly a UAV in a professional application. And for that, we're going to hear first from Jan Leesens from Air Robot. Jan, please proceed.
Thank you, Alan. From Aerobot, we are a startup company in Belgium, and we focus in making applications to turn drones into flying robots. What are we trying to do? When we talk to people in the drone industry and we talk to people in the real industry, we see a big mismatch between what people expect from the technology and what the technology is able to do. And we are trying to bridge that gap. But first of all, I want to go very quickly back to the basics. Why are people interested to use a drone? First of all, it's to reach areas that are difficult or expensive dangerous to reach by humans, to inspect or measure certain types of infrastructure, or to get an overall view from above for mapping, 3D rendering, site supervision applications. And if you talk to people, why do you want to do that? We often think it's about cost, but if you talk to people, for example, in the professional and industrial inspection industry, they say we actually want to be able to do more inspections than with people with rope access technicians, for example. We want to make sure if we inspect the infrastructure, we have to say we can minimize downtime. It has to be safer than we can do today, and they also have a problem collecting objective and consistent data today. I've spoken to people from a utility company, and they said that when it rains, their inspectors report less problems than when the sun shines. So an automated solution using drones can be of very, very big value for them. There are lots of applications for drones in areas to monitor areas that are difficult to reach. There's the high voltage towers, there's the bridges, there are industrial sites, and there, as you see from the numbers on the slides, there are really a lot of them. So you wonder, why is this industry not picking up faster? Well, if you speak to people who run these businesses, they say, okay, yeah, we are convinced the drones will be a disruptive technology. However, we should be able to collect, data that we collect today at a lower risk, at a higher speed, and we don't want to add complexity to operations. And especially the last point is often a problem. On this picture, you can see an inspection of a cement factory, and you see the drone in the middle of the image, and there you immediately see what the challenge is to fly the drone. The pilot is behind the drone, and he has to fly at 5 to 6 meters to take sharp and high-resolution pictures. Because the pilot has a very bad visual, a view of how far the drone flies from the building, they use a third observer who looks at it at an angle. So it means that it's quite a complex setup. They need to have 3 people who get access to work on site. It gets more complex, more expensive. And so the people who operate this factory say, okay, yeah, drones is nice, but it's not yet for us. So what does need to be changed according to us? First of all, drones should fly more safely. They shouldn't fly into something. They shouldn't fly away if there's something, but they shouldn't fall out of the sky. And unfortunately, the industry made a huge progress last year, but unfortunately, YouTube is still full of these sites, and those are the sites that are viewed by the security managers and for these sites. Drones should fly more accurately, and the data should be of a better quality. I've known people who said, okay, we tried the drones, but up to 25% of the images were not sharp or out of focus, so we cannot do anything with the data. Or they say data, if they fly, for example, next to a high voltage tower, drone comes back with 100 pictures, all labeled DSC0016, D0017, and there are zoom ups, so the maintenance crew has no idea where these pictures were taken. So if these images are not taken and are properly georeferenced, they're also not worth a lot to the people who want to use it. And finally, drones should be able to fly more automatic than they are today. And note I mentioned automatic and not autonomous, because there are a lot of situations where a human pilot will be needed to act if there's for example, if there's a police helicopter flying over or a flock of birds is passing by, to take action in an exception and to make sure the whole operations are safe. And that's according to us the role of the pilot in the future, while the drone should do the data collection automatically. And typically a drone will be able to do it better than a human pilot. So how do we do that? Let's say we start from an existing drone platform and we add technology to that. We add collision avoidance technology. We add accurate and non-jumpable positioning solutions from a well-known supplier. We add smart navigation. We add real-time communication to talk to the drone and download all the information. And we create software to make sure that the whole workflow can be integrated with the work process of our customers. And for each of these fields, the choice of technology often depends on the application. A very good example is the sense and avoid technology that's available. There are three main technologies that are used today are based either on stereo vision, on two cameras, looking at the same obstacle and trying then to determine the range using image processing. That's a technology which has a good range. It can see very far, but it has problem detecting objects that have very few visual features. For example, a white wind turbine blade, a concrete wall, a tree. Also, if there's a glare in the lens caused by the sun, it won't give a solution. So it's not always the most reliable solution. Laser systems, they have a very good range, but typically they have a very narrow field of view. So that makes it difficult to detect open structures like high voltage towers and cables. Ultrasonic technology, which we use typically, it has a wide field of view. It can detect open structures and cables. However, the range is limited. So really, depending on the technology, or depending on application, we have to choose the right technology for sense and avoid. Then, looking at the GPS technology, anti-jamming is very important. This is a test that was done by September using the simulator. And on this picture, you can see the effect of a jammer on three different receivers. So the red one is the typical receivers that are integrated on the drone right now. The green one is a high-end receiver from another manufacturer, and the orange one is a September receiver. And as Gustavo mentioned, is that when the drone approaches the jammer, the signal quality drops. The high-end receiver loses position, but it doesn't provide the wrong solution. But the standard receiver, it gives errors that are 20, 30 meters off. And if you are using GPS to navigate your drone, which most of the drone manufacturers do, this can be lethal, especially when flying close range next to a building. And in Belgium, typically we have quite a lot of problems with this because in April last year, the government introduced a road tolling system for trucks, which is based on GNSS. And suddenly more of these devices are appearing. And also, of course, where do they build all the wind turbines in Belgium? Next to the motorways. So this is a real danger for UAV operations for wind turbine inspections. Another aspect that needs to be taken into account, according to us, is the design of the brain of the drone. There is a tendency to try to put everything on one small computer, and that has a disadvantage if you have a software. If you have a software problem that you lose control, that the drone flies away, that just falls out of the sky. According to us, a drone brain should still be designed as if the drone is an aircraft. If it is an accident, of course, you won't have a huge amount of casualties, but these drones, they carry expensive payload and they fly close to even more expensive infrastructure. So the piloting has to be designed for for safety and reliability. We see the approach that a bit like a human brain has developed over the centuries. There is a basic flight controller that keeps the drone in the air, takes care of the engine control, the flight stability, and so on. You have a section that is responsible for the survival skills like sense and avoid, geofencing, that kind of stuff. And then all the payload processing, smart navigation, and so on can be on a different CPU. And why is this? Because if there's a crash in the most complex part of the software, there always be control possible of the drone. The drone won't fly away, and so on. And that's really important and key for industrial applications. So what we do at Aerobot, we have we help two kind of customers. The first ones are drone manufacturers and drone operators who want to add technology to their drone. There we provide distance measurement technology. We integrate active sense and avoid on drones. We integrate the RTK for navigation. So we can add this to almost any drone that's available in the market, especially all platforms that are based on DJI and Pilot. But let's say the majority of our attention goes to what we call the distance industry, where people would use drones for inspection and mapping applications. There we help our customers to select the drone they need and apply the technology that's needed to operate it safely in that application. One example is, for example, an extension kit that we built for Falcon 8, where people wanted to operate it for close-range inspections, for example, for a cooling tower. And there we added both our ranger for collision avoidance and distance measurements, and added the RTK GNSS to georeference all the images that was collected. And with this tool, people can not only avoid collisions and get georeference data, they can also measure in the images that are collected. On this slide is an example of a picture taken next to a monument, where we calibrate the images based on the range to the building, and allow people to measure with millimeter level accuracy in the images without actually having to go and put a ruler next to the building. And that's very important for building and bridge inspections, where people want to follow up, say, a specific problem multiple times in a year. They can fly back and check and see if there's a crack, for example, that's evolving. So if you need help to turn it into an Aerobot, let us know. Contact me or follow us online. So if there's anything, let me know, and I'll give now the floor back to Alan.
Thank you, Jan. And at the end of our webinar, all those in the audience will be able to see email addresses to contact the speakers directly with questions about applications or anything further. We are going to turn now to another drone, another UAV manufacturer and operator, this time more specific to surveying and mapping. We're going to hear from François Gervais from SenseFly, leading UAV manufacturer and provider. François, please take it away.
Okay, thank you, Alan. Yes, flying drone is one aspect, and generating quality results, accurate results is another aspect. Let me move to the next slide. Okay. So I adopted drones about 7 years ago, and piloting was one challenge. Creating accurate results was another challenge. And I'm pleased to explain a little bit how we work with our new EB Plus here and create photogrammetric accurate results. Okay. So the EB Plus has several features. And one of them is perfectly related to GNSS, which is the upgradable RTK PPK, what we call the high precision on demand. There are other aspects like extended flight time, having a very specific photogrammetric dedicated camera, and a piece of software which is called Emotion 3, and several different options, camera options. You will see that the software that is used during the flight, for the flight preparation, during the flight, and after the flight is very useful as well for this post-processing, for the post-processing part of the project. So SenseFly has a long tradition of drones since 2009. They have always been safe and efficient, and we added a few additional features now with this newly released EB Plus, released in 2016. There is a few aspects here on this slide, and I will focus the presentation here on the RTK, PPK capability of the drone. Okay, yeah. So over the next slide, I would like to present 3 benefits for the user, for the end user. And the first benefit is this survey grade accuracy that you will get straight from the drone. And as Gustavo mentioned earlier in this webinar, knowing the exact position of the GNSS antenna is one thing, and then knowing it at the time of the exposure is very important as well. Synchronization between GNSS antenna and camera is essential. Another aspect is a tight integration between GNSS antenna and the camera. There is always a small lever arm of a few centimeters, maybe up to a decimeter, but you have to take this into account if you want high accuracy in the end. And one important thing is to remember that you have a scale factor between the camera, the camera system, and the terrain system, the ground system. You have a scale factor of about 10 to 30,000. So anything that will be wrong in the camera system will be amplified by a factor 10, 20, 30,000 in the end on the ground. The compromise that we choose was to measure accurately the position and to compute accurately the angles. This is the compromise, cost, weight, power consumption compromise. And in the end, what we get is an accuracy of 2 to 5 centimeters and angles, computed angles of 100 to 500 of degree. Okay. Right. So how does this benefit translate in the real world? And we have here a recent example that was made in California by an EB user. You have the details here, and what is interesting is the testimonial that he gave at the end of the work, and he said that going down to 1 to 2 inches in American language, which is exactly the accuracy that we will get from our GNSS of our RTK PPK solution, in both vertical and horizontal, was just excellent and ideal, and it's not what you would expect from the aerial mapping. It's more what you expect from a terrestrial mapping. But now you can get this accuracy from the air with all the advantage that you can imagine. So the second benefit for the user is the workflow flexibility. Trying to provide one workflow and apply it to any situation is just impossible. So what we choose is something very flexible and very adjustable to the current situation. So depending on the operator, you will choose the precision level and the according workflow for a particular mission. And it's interesting that the same operator will choose different scenarios, different workflow for different missions with the same hardware and software. And this is where the RTK and PPK come into play, depending if you have a base station available or not, if you have a virtual reference station, an RTK stream available or not, if you have a continuous operating reference station available as well, then you will choose one or the other. And the end effect of all this flexibility is minimizing the number of ground control points and turning to just checkpoints. And we will see the difference the impact in a few seconds. And an interesting point as well is we talk to surveyors, and they already have some equipment. They have a base station. They might have a subscription to a VRS stream, for example, and they want to reuse it. And here, having a flexible solution from a GNSS point of view is really important. And it works very well, and we see some trends which are different from one country to another, and all the aspect of the workflow has been used so far. And one important thing that I will mention, I will explain more in detail in a few seconds, is the fallback option. There was a long discussion over the last few years about RTK. Is RTK the ideal solution, the unique solution for every situation? RTK is ideal when it works, but you cannot guarantee 100% that it will work. It could be some reason you will have you could have some problem, connection, availability, equipment, missing equipment, or whatever. So because of that, nobody's perfect, and what I mentioned, the Murphy's Law here, you need to have some fallback. And this is how it's how you will achieve your high absolute accuracy with this flexible workflow. And we have here, I hope that it's nicely readable. It's a simple decision tree that will, in 3 questions and answers, you will be able to decide what type of survey, what type of flight you will do in order to get your high accuracy. And there are several options. The first one is, do you have a drone that is RTK, PPK capable, of course? If not, then probably you will be back to just having ground control point. If you have one that is RTK capable, do you have an RTK stream available, which will be the simplest solution, maybe the most sophisticated solution, but the simplest solution in the end. I mean, with the less logistic. If you don't have this available, then do you have a base station available that you will be able to connect to your ground control station and then stream RTK correction? And if all these options are not available, you still have in the end the PPK, the post-processing option that will mean the little additional work in the office, but you get your final accuracy. However, even if everything was not perfect during the flight. So having this flexibility guarantee that in the end you get your surveying accuracy. The third and last benefit that I would like to present is, of course, a time and cost savings in the end. Considering that you need a 3D absolute accuracy, and if you fly a non-RTK PPK drone, then you will need ground control point, and the ground control point will cost time and money, of course. And from my experience as a service provider, I had this few numbers here. Setting up one GCP costs about 10 to 20 minutes. Including going there, choosing the location, signalizing it, measuring it, and going to the next one, which is a cost of about $60 to $80 US. So if you consider that for any project, any small project, you need a minimum of 8 ground control points. It's 1 to 3 hours that you will spend on that, which is a cost of about $500 US just for this part of the ground control point. And it's something that is useful for a few minutes, just for the duration of the flight, and then it's gone. And it requires vehicle, GNSS, base station, and some experience. I mean, it's not completely easy job. So it's not simple. The location and the distribution of this ground control point is essential. So again, this experience, and it brings some constraint on the workflow. It requires additional office work because you have to click, you have to measure in your images your ground control point. So eventually, the advantage of checkpoint is huge in the sense that it's much less demanding. You need less in terms of number, and you need the location of these checkpoints is less critical than for ground control points. And to conclude, I have here a quote from a well-known surveyor in Ireland, and this is really specialized in quarries, and he mentioned a nice job for 88 hectares, so a little bit less than 1 square kilometer. It said, okay, the whole job took 4 to 5 hours, and but out of these 4 to 5 hours, 2 to 3 hours were used just placing the control points. So you can see having high accuracy GNSS, RTK, PPK, GNSS in your drone can save a lot of time. And can save up to 50% of your field time, and then have a much better efficiency in your workflow. This was my conclusion. Thank you. I give you the word, Alan.
Thank you, Francois. As you've heard Francois discuss the RTK, and we'll return to that a little bit more in the question period at the end. Right now, we're going to move on to Zach Casas, who is a professor at the University of California, Riverside, and he has been exploring the problem of what do you do when GNSS is not available for your UAV, and this can often be the case. Zach, please give us your presentation.
Thank you, Alan. Welcome everyone who is attending this webinar. And as Alan said, I am an assistant professor in the Department of Electrical and Computer Engineering and University of California, Riverside. And I'm also the director of the Aspen Lab, the Autonomous Systems Perception, Intelligence, and Navigation. And those are my students, PhD students, master's student, and an undergraduate student. And one of the things that my students and I have been looking at in the Aspen Lab is how do we navigate in the absence of GPS or GNSS more generally. So our approach is to exploit whatever radio signal of opportunity that exists in the environment. Obviously, these signals of opportunity are not intended for navigation, so there is a lot of work to be done to be able to robustly and accurately navigate with them. Those signals include, let's say, Iridium satellite signals, AM/FM radio, Wi-Fi, cellular with its different standards, LTE, CDMA, or even digital television signals. So the idea is to build software-defined radios that will enable us to navigate with those signals and eventually evaluate the performance. So why cellular signals of opportunity are particularly attractive? Well, first of all, they are abundant. We have many, many cell towers around us from different providers, different competing providers actually. They are available at varying geometries and frequencies. They are practically free to use. So our approach is to exploit those signals in a one-way communication fashion. So we are eavesdropping on the tower, so to speak. The tower doesn't even know that we are using its signal. We are not a paying subscriber to that channel. And those signals are significantly more powerful than GNSS. We are talking here 20 or more dBs higher. So they are available where GNSS signals are typically severely attenuated. However, there are still challenges to be addressed before we can use these signals for reliable and accurate navigation. One is that the states of these towers may not be known a priori, so we have to estimate those states. We can't find on the market a navigation receiver that is capable of telling us where we are using these signals. So these receivers that will produce what is called observables for those of you that work in the GPS or GNSS domain. Those are the pseudo-ranges and the carrier phase. So we need to extract those from those signals. And their clocks are not as stable as the atomic clocks on the satellites, on GNSS satellites, nor are synchronized. So those are issues that have to be dealt with. And finally, since this is a new paradigm, we don't have error budgets like GPS, for instance, that tells us the different sources of error and how well we can do. So one remaining question would be, well, how well can we do? And this is what I will show you next. So first, let me introduce the workhorse that will enable us to navigate with those signals. And this is really a software-defined receiver that my students and I have been developing that we call MATRIX, which is a short acronym for Multi-Channel Adaptive Transceiver Information Extractor. So MATRIX has different modules. Each module is dedicated to a particular type of signals of opportunity. What you see here is the cellular CDMA module of MATRIX, and you see the different virtual instrument realization. So we are developing this partially in LabVIEW. So those are the different VIs corresponding to the different modules or the different phases for the cellular CDMA module. And what you see here is a graphical interface that tells us what is happening inside the receiver. So this up here is the signal acquisition. It's very similar to GPS. Obviously, GPS is also CDMA. So you see the correlation peak parameterized by the code start time, Doppler frequency. This is the carrier to noise ratio, and you can see, it's more than 60 dB hertz. It's significantly more powerful than a typical GPS signal. This here is the signal tracking, and you see after a short period of transience, we are tracking the signals. This here is message decoding that we perform for data association purposes. So there are a bunch of videos of our experiments on YouTube, and you can just search Aspen Laboratory on YouTube. We have a YouTube channel with experimental videos, or you can also find them on our webpage, Aspen, on the Aspen webpage. So this is one of the experiments that we did where we navigated a UAV with cellular CDMA signals. So in this particular framework, the way we did it was we put what we call a mapper, which is basically an antenna on the top of the roof of our building that had access to GPS and whose task was to estimate the clocks of different base transceiver stations, cellular base transceiver stations in the environment, and share those clock estimates with a flying UAV, which we call the navigator. Okay? So in this particular situation, we only used 2 base transceiver stations. Now, the navigator knew where those base transceiver stations, but it didn't know their clocks, so that mapper was helping it by giving it its clock estimates. What you see here in white is the navigator's trajectory that the UAV traversed, and we extracted that based on the UAV's onboard navigation system. So this is the GPS and inertial navigation system and other sensors. The green is the trajectory that we estimated only with cellular CDMA signals. So this is nearly half a kilometer, and the root mean squared error, which is the difference between the GPS and the cellular CDMA, was on the order of 9 meters. So we are doing pretty well there with only 2 cellular towers. The next thing that we looked at is exploiting LTE signals. Okay, so that's looking at the 4th generation and later. And what you see here is the LTE frame structure, and basically there are 3 signals that we are looking at: the secondary synchronization signal, the primary synchronization signal, or PSS, and the cell-specific reference signal, or CRS. Okay? The beauty about CRS in particular is that it has a very large bandwidth. It's up to 20 megahertz, and it is transmitted by cellular towers to estimate the channel. So we are going to exploit this CRS signal because it's going to help us alleviate multipath. Now, one challenge with CRS is that you can't use a conventional DLL, but there are ways around that. And without going into too many details, all of the details are in our technical publications that you are welcome to look at. But this is a very high-level, let's say, view of the 3 virtual instruments corresponding to the cellular LTE module of the MATRIX software-defined receiver. This is a block diagram of the receiver itself, and the more exciting thing is to see how well we can do with cellular LTE signals. So we equipped the car with GPS and LTE antennas, and we traversed this green trajectory. We had access to 8 GPS satellites at the time, and those satellites were in, let's say, good visibility conditions. So multipath was not an issue here. We were listening to 2 E-Node Bs. This is what is known as the LTE base transceiver stations. Okay, we only had 2 that we used. One was 930 meters, one was 720 meters, and those signals did experience multipath, okay, whereas GPS didn't. And the question is how well we can do. So what you see here is after correcting for, the bias and the offset between the GPS pseudo-range, the SSS, the secondary synchronization signal pseudo-range, and the CRS, the cell-specific reference signal, you see that the GPS and the CRS are in very good agreement. However, SSS only, which one would exploit using conventional delay-locked loops, it has these spikes. Now, this is going to introduce a lot of error in your navigation solution. So we took a closer look at why do we have this, and really the CRS signal is what helped us answer those errors. It helped us estimate the channel impulse response, and you see here the different peaks corresponding to the line of sight and the non-line of sight signals that we are receiving. So we are using CRS now to estimate the channel impulse response and use that as an extra feedback in our cellular LTE receiver. Those are navigation results. The white is the GPS solution with 8 satellites. The green is the CRS solution, and you see it is pretty much on top of the white. So for part A, you see that the root mean squared error, this trajectory is nearly 2 kilometers. We were 9 meters in root mean squared error from a GPS solution with only 2 LTE transmitters, okay? However, SSS was all over the place, and multipath there was an issue. Then we took this receiver into a more challenging environment. This is in downtown Riverside. Those are the 3 cellular towers that we used. We traversed a trajectory that is longer than 1.5 kilometers, and the error that we obtained between the solution from those E-Node Bs and GPS was around 12 meters, okay? So the punchline here is LTE offers us this large bandwidth signal, which is CRS, that would help us alleviate multipath if it is an issue for us. Okay, and then we moved into aiding the inertial navigation system with cellular signals. So as we all know, UAVs typically don't employ just a standalone GPS receiver to navigate. It uses the GPS receiver in conjunction with an inertial navigation framework in some coupling fashion, whether it is loosely coupled, tightly coupled, ultra tightly coupled, and so forth. The problem is if you have jamming or spoofing or interference, the thing is if you lose GPS, your inertial will start drifting, and the rate of that drift is really a function of the quality of your inertial measurement unit. So what we are saying is no GPS, no problem. GPS gets jammed, spoofed, or lost for one reason or another. We will aid the inertial navigation system with cellular signals of opportunity, and we will do that in what I call a radio SLAM fashion, a radio simultaneous localization and mapping fashion. So here I'm removing the requirement that I need to know where the towers are. I will simultaneously estimate where the towers are together with the UAV state, and I will aid the inertial navigation system with GPS when it's available, and when it's not available, I will use cellular signals of opportunity to aid my inertial, and I promise you that I will get experimental results that are very, very close to standard GPS. So this is a simulated environment to show you what I mean. I have a UAV that's going to go and take this orbital trajectory around downtown LA. After it finishes the first orbit, I will cut GPS, and I will have the UAV aid its inertial with 4 towers that we had pre-surveyed. We know where they are, but the UAV doesn't know where they are, and the UAV will simultaneously estimate where they are together with its own state. So those are simulation results. You see here on the left the drift in the inertial navigation solution. Basically, it's dead reckoning at that point. We assumed that the UAV had consumer-grade IMU, and you see the drift after the UAV lost GPS signal. On the right, you see the aiding, okay, with cellular CDMA or LTE signals. It doesn't matter at this point what type of a signal we are receiving. And we are maintaining the circular orbit that we had commanded the UAV to follow. So those were simulation results. This is here a zoomed version on that trajectory, and you see here the drift. This is the red trajectory when you cut GPS with inertial only, and this is the scary part about relying only on GPS, whereas the green is what we are able to produce by aiding the inertial with cellular signals. Okay, we are maintaining the white trajectory that we had commanded the UAV to follow. On the bottom, you see how well we can estimate simultaneously the location of those emitters or of those towers. You see it happened to be, one of the towers happened to be on top of one building. This is the estimate, and just by it, you know, within less than a meter or so, or maybe 2 meters, we had our estimated location, and the yellow circle or ellipse is the uncertainty about our estimate. So this here just shows you extended Kalman filter results, and you see when you cut GPS, your errors start accumulating and you will drift, basically, whereas we are able to constrain that error. And finally, this here was the cover of this month's issue of GPS World magazine, and here we are showing real experimental results. We have 5 towers that we are exploiting, coming from 3 cellular CDMA and 2 LTE. We cut GPS, and what you see here in red is the unaided inertial navigation system solution. It starts drifting, and within 40 or so seconds, you have your errors more than 100 meters in 2D, 3D, and even the final error. Okay, so this is a consumer grade. This is a DJI drone that we use. Whereas in another situation, we cut GPS and we started aiding the cellular, we started aiding the inertial navigation system with cellular signals from our matrix SDR, and we are able to constrain those errors to 4.68 2D RMSE error and 7.76 3D RMSE error, and the final error was around 5 meters. So last but not least, I would like to acknowledge the funding agencies for this research, the Office of Naval Research, to whom I'm very grateful for, the National Science Foundation, and the University of California system. And you can find all the technical details and videos of our experiments on the lab's webpage. And that concludes my presentation, and I will give it back to you, Alan.
Thank you, Zach. We're nearly at the top of the hour, but we do have some extra time that we can take advantage of. So we're going to turn to some questions now from the audience, and we'll deal with 2 topics generally. One, as is the case with almost any GNSS webinar that I've hosted over the last 3 or 4 years, people are asking about jamming and spoofing. Now, Zach addressed one remedy in his presentation just now, but Gustavo and Francois, can you tell us about encountering jamming and spoofing in your business applications, professional applications, how often it happens, what are the remedies, and what's the outlook for future operations? The questions that came in from our listeners were specifically, has the security of signals being addressed to avoid jamming and or hacking UAVs or drones been addressed, and particularly spoofing in the UAV context? Gentlemen?
Yeah, so I can take that, Alan. For the jamming side, I mean, you will have 2 types of jamming. Of course, you will have intentional jamming and non-intentional jamming. Unfortunately, many people might not even realize about it. The problem is that, of course, your signal will be maybe wrong, and then you might not have a solution, but you don't know what is the reason of it. So, as I mentioned, the best, of course, is to try to have these techniques that allow you to mitigate those type of problems. Spoofing is a bit different, of course. For spoofing, there are one of the questions that I also saw popping up is if the signals are already providing you certain information in order to avoid that. You can consider in signals such as Galileo as an example. They will have a service that will have an authentication of is the signal coming really from a satellite or is it coming from a spoofer system? So there are, of course, technologies coming in that side, but spoofing is a bit, of course, more limited. For jamming, I think is a reality. The jammers that you get to see in the field could be from the transport industry. Many people put actually just a jammer in order to avoid, for instance, the quotes that they have to pay in the transport. So it's happening more and more, and at least this is what we get to see. Once that we get the data from our customers, we say, oops, this is actually related to a jamming part of it. I don't know if Francois has some experience also in that side.
Yeah, it's a bit different. I mean, we are just integrators, so we have to rely on the technology. But I would say jamming, we have to consider our own jamming. And it was mentioned that there is a lot of technology in a very small volume, in a very small space. And I would say this is the main challenge from an integrator point of view, is to handle our own jamming between cameras, antennas, sensors, power supply, and so on. And from my experience, maybe we are in a lucky, safe, and peaceful environment, but we haven't experienced any jamming to the point that we were not able to fly, or that I would say the safety was in question during the flight. Back to you.
Thank you. Secondly, a number of listeners want to know more about RTK. Francois covered that in his presentation, but some questions have come in concerning the availability of low-cost RTK-enabled GPS for UAV-based data collection. How can RTK services help? Well, Francois did cover that. When is RTK required? If you'd like to discuss those, any aspect of those questions, RTK generally.
Yes, of course. Okay, maybe just quickly. RTK is really the ideal solution. I mean, you have actually before the flight, during the flight, and right after the flight, you have the confirmation that you know exactly your accuracy. So it's really the ideal situation. It's just that the reality says that you cannot rely only on RTK. You have to have this safety net of post-processing. But RTK now is really from the efficiency point of view, it's really great. And so many countries have now a very efficient virtual core system that can so continuous operating reference station that can provide a virtual reference station anywhere in the country. It has a cost, of course, but it's really, from an efficiency point of view, it's really the ideal solution.
Yeah, I can try to expand a bit on the usage, of course, of RTK. Of course, one is very important, as Francois mentions, is the mapping side. But we also see the need from different people to try to use now RTK not only for mapping parts, but also even for the landing or for the hovering of the drone. So there are different applications that are actually becoming more of a reality. And I think that's actually what will happen. Mapping was already, is starting to be addressed and is becoming really mature in that market. And what you will get to see is much more real-time RTK usage in the UAV industry. So this is really happening, and the questions are already passing by. Your question was also in the difference between high-end GPS receivers and possibly the consumer-grade GPS receivers, which will be the low-cost GPS receivers. As I mentioned, of course, the technology is quite different. You have to take into account that it's a multi-frequency GPS receiver, the one that will give you really the centimeter level accuracy. And even if some people tell you, okay, my GPS receiver is already a multi-frequency, that does not mean that it's actually a simultaneous frequency that they can track at the same time. So you might not really have the same benefits of some of those systems. Another aspect could be also the initialization of the RTK, the measurement quality that you get from those GPS receivers. There is a baseline dependency. Where is your base station located? Cheap GPS receivers might not be able to go for long baselines as well. And well, there are other effects already that are tackled by RTK, such as ionospheric disturbances and much more. So, of course, you need to find what is really the more important thing for your application. But as I mentioned, we have seen really a boost in terms of the demands on centimeter reliable RTK systems.
Thank you. Final question, third question, this time for Zach. Somebody wants to know, why only LTE? Why is this navigational aiding not possible on legacy or also known as 2G networks?
Okay. Well, I started the presentation by talking about another that's soon to be legacy, which is 3G, which uses CDMA. It is still also possible on 2G networks if they are using CDMA. Such as GSM. GSM uses TDMA, and this is possible. We didn't pursue this recently. I looked at this some time ago. The thing is, TDMA and LTE will give you better accuracy due to the signal characteristics themselves. But that doesn't mean that you can't use 2G. It is something that we are not currently pursuing because we don't feel this is the future. But as I said, some 2G networks use CDMA, at which point you can use the CDMA receiver that we developed as is. Whereas if you are looking at 2G with TDMA, then you will have to develop your own receiver, or you can look at some of the publications that I did back in my PhD days.
All right. Thank you, Zach. Well, I want to thank all of our speakers, all four of our speakers, for lending us their expertise today. I want to thank the audience for joining us. Attendance stayed steady throughout, showing that we have, it's always good to see from our viewpoint, showing that we've pitched the content right. You can see on your screen contact addresses for our four speakers, and we encourage you to follow up with them. We encourage you also, you'll receive an email within the next day or two notifying you that the webinar is available for download. We encourage you to share this with your colleagues. Access to the webinar content is free. You need only register yourself, and you can have access to this and all the other webinars that are archived on our website, many of them dealing with UAVs. We'll have another webinar next month, sponsored by Terrago, and it will cover specifics of mapping and new mapping software and hardware. We encourage you to look for that. You can go to gpsworld.com/webinar, and in the next day or two, the registration page for that will be open. Thanks once again to our speakers. Thanks to Kelly for running the boards on this. Kelly, back to you.
Thanks, Alan. And I'd like to thank everyone again for attending today's webinar. And like Alan said, if you have any more questions, don't hesitate to reach our presenters at the emails on your screen now. Links to their email addresses are also in the bios to your left on the console. You can download today's slides using the download box on the left side of your console. And finally, as Alan said, an on-demand recording of today's webinar will be emailed to you tomorrow afternoon and will be available online for a full year at gpsworld.com/webinars. We look forward to seeing you at a future webinar. Bye.